Okay, so we'll make yet another digression. We saw that what we wanted was the graphs and fundamental groups of graphs to understand covering spaces. Fundamental group turns out to be a free group. So we want to understand what are free groups. So suppose we take S as a set. So free group S, f of S, so is a free group on S. We'll call it free group generated by S. What is it? It's essentially is the group which has basis S, in the sense that it has the same relation to the group as a basis has to a vector space. Okay, so let's recall what that relation is. So for that, we'll fix a vector space and a set which may be contained in it or included in it. Okay, so let's take a vector space and S a subset in it, or you could even rewrite this if I had an inclusion map from S into V. So then S is a basis if the following happens. Okay, so for W vector space, if I know a linear map on F, so on the set S, so let's say F mapping S to V, W, there exists a unique L mapping V to W linear such that L of S is F of S for all S in S. Okay, or if you want to think in terms of inclusions, I have an inclusion, I have V and I have W. Okay, and from here to here we have that would be a solution, so I should dash it. Given a map F here, we have a solution to this, but this is not quite the same commutative diagram, because strictly speaking this map L requires V and W as vector spaces, while I and F depend only on the underlying sets. So when we generalize, in fact we generalize to what are called concrete categories. Okay, so we'll make an exactly parallel definition for the case of free groups. Okay, so let's do that. So our basic setup is free group generated by f of s, let's call it, or we just call it f, is a group f of s together with an inclusion map such that the following happens. Given another group, let's say H a group, and given a map at function level f from S to H, there exists a unique map which is phi from G to H, but of course not just a function, there exists unique homomorphism such that if I look at for all S in S, phi of S is just f of S. Okay, that is, if I look at S and it's included into my free group f of S, and I have a map to H, then there's a homomorphism so that this one commutes. This is called f and this is phi. Okay, so that can be written as f is phi composed with I as maps of sets. Okay, so this is nice. So we have a free group. It's a group with a basis, namely that if I have a map on the basis, I get a map on the whole group, and as this map is unique. Let me take a quick example. There's one free group we know, which is that Z is a free group generated by 1. Okay, this is what you would see in a first course in algebra, namely if I know the value of Z on 1, so if I'm given F which maps the singleton 1 to H, okay, we get phi which maps Z to H, and not hyperbolic plane, sorry, just the group H given by phi of n is going to be f of 1. Now H may be non-abelian, so I should use multiplicative notation here to the power of n. Okay, and this is unique because this is the only map. So we do know free groups on one generators, but unlike vector spaces where all vector spaces have bases, at least assuming axiom of choice, most groups are not free groups. Free groups are a rather special construction. Other than Z, unless you set out to construct a free group, it's not likely that you'll encounter a free group. We don't actually know that such free groups exist, but as happens somewhat perversely, we can prove uniqueness. That is, if it exists, there's only one such free group with basis S. In fact, uniqueness in a strong sense. Okay, namely, suppose we have two different free groups generated by S. So let's call them F prime of S and let's say F double prime of S, or maybe I'll just call one of them F of S. Are free groups with I don't call it, it's not formally called with basis, it's called generated by, so generated by S, and we have the corresponding inclusion maps. I prime maps S to F prime of S and I maps S to F of S. Okay, so theorem is there isomorphic. Okay, there exists a phi from whichever direction I want. Let us say F of S to F of S prime, F prime of S, and this is an isomorphism. Okay, so and in fact it's an isomorphism which respects the inclusion maps. So I have I here and I have I prime going to F of S and I have this going to F prime of S, and this commutes. So this is an isomorphism. So not only are they isomorphic, they are isomorphic in such a way that the basis is taken to the basis pointwise, not just as a set. Okay, and this is a general idea. If you define things by, this is the free group we saw is an example of what's called a universal property. If you define things by universal properties, then they are automatically unique if your definition is correct. And the following argument we'll see in many contexts if you have not seen it already. Namely, suppose, so we'll use the universal properties. Okay, so as F prime of S is a group. Okay, let's push this statement aside, and F of S is a free group. Okay, so we are given I prime, this is a map from S to F prime of S. There exists phi mapping F of S to F prime of S, and this is going to be a homomorphism with, if you recall, if I look at phi composed with I, this is going to be I prime. Okay, so if I have the map I prime, which is an inclusion on sets, I get a full inclusion, and that inclusion has the property that on the set, if I include an element into F, I includes it into S, into F of S, and then we map it to this. Okay, so similarly, as F prime of S is a free group. Okay, and this time we are given the map I, and this is a map which maps S to F of S. So this is just a function. So I've been saying map, I should clarify these are sets, so there's no topology here, or you can take discrete topology. Anyway, these are functions. So similarly, as F prime of S is a free group, there exists a homomorphism, let's call it Psi, which is going to be mapping in the other direction, F prime of S to F of S, such that I is Psi composed with I prime. Okay, so that's nice. So now we have a map from here and we have a map from here. Okay, now we want to show that phi and C are inverses of each other, and I'll show one because the other is very similar, and here there's a very neat way of doing it. Okay, namely, let's look at the following diagram. So we have S, we have S which goes to S prime. Oh, sorry, we don't have S going to S prime. We have S, which is mapped by I to f of S, which is mapped to f prime of S, and which is mapped by f of S again. Okay, so here we have I prime, and here we have I, and we have this map which we call phi, and this map we call C. Okay, notice we haven't used uniqueness yet. So what is this map? This is phi composed with C. Okay, so now the left hand side is a free group and the right hand side is a free group itself. That is, the f of S is a free group and f of S is a free group. Okay, so there exists unique homomorphism. Okay, let's call it eta or something like that, which maps f of S to f of S. Now I'm treating f of S as a group, okay, such that eta composed with I is I. Okay, so that is the universal property. This time I'm taking f of S as the target group and inclusion itself as the function. Okay, so there's a unique homomorphism, eta. I called it eta temporarily, but you can actually see there are two different concrete homomorphisms. Note, eta equals phi composed with C is as above. That's what our diagram shows. Okay, as is, of course, there's an obvious map, identity, on f of S. Okay, hence, by uniqueness, phi composed with C is the identity. So what we did is we solved our two separate problems and then noticed that the solutions of the two separate problems compose to give you a solution to the universal problem where things are kind of trivial, where the target group is f of S itself and the inclusion map is the given inclusion itself. Okay, but then identity is also a solution, hence the composition has to be equal to identity. The reverse is exactly the same argument with f and f's roles reversed. As a result, we get the rather nice situation where your construction is unique, even though we don't know if such a free group exists or not. Okay, so our next task, which we'll turn to in our next segment, is to actually construct an object called a free group. A general warning here, this definition works in any category which is nice enough. Okay, what's called a concrete category, because we need to identify objects with sets. But the free objects may not exist. We'll see examples later of this, that free objects may not exist. But if they exist, they're unique. That's what we know.